Hello, my name is Nicola DeMarinis. I'm from Somers, New York, and my project is on characterizing asteroids using photometric data. Asteroids are small rocky bodies that orbit our sun, and there is an estimated 150 million asteroids in our solar system alone. And out of that 150 million, roughly 1 million asteroids are known in our solar system, and only a small fraction of those known asteroids have shapes and shape models generated for them. There are two main ways for generating shapes and shape models for asteroids. The first being light curve photometry, seen here on the left of the slide. Light curve photometry occurs when an astronomer observes an asteroid rotating around its central axis for a long period of time, usually 7 to 10 hours. And from these events, astronomers can then characterize that asteroid, generating shape models. On the other hand, asteroidal occultations, which was the exact method that I used for my project, occur when the light from a distant star is occulted or blocked by an asteroid. This blocking of the light creates a magnitude drop, which can be seen here in the center of this image. Also, that blocking of the light creates a shadow path on Earth from which I can then characterize that asteroid. Asteroidal occultations are important for many reasons, as they, firstly, help astronomers understand the formation of terrestrial planets, which are essentially Earth and Mars. They also help astronomers provide insight on the formation of dynamical families, which are groups of asteroids in our solar system that have near identical properties. They also teach us about the origins of the solar system and the emergence of life on Earth, as asteroids are largely credited with bringing the heavy elements and water to Earth responsible for the emergence of life. In the asteroidal occultation field, there was a key association known as the International Occultation Timing Association, or the IOTA for short. Now, the IOTA provides the necessary softwares for observing and then analyzing these events. These softwares include Occult Watcher, PyMovie, Pyote, and Occult, all of which I will talk about more later. In the analysis process, I used the database of asteroid models from inversion techniques, or DAMIT for short. Now, I use this database in the occult process when I am comparing my observations along with the observations of the other astronomers, and I am refining a pre-existing shape model in the DAMIT database. For my project, I set up three main objectives. The first being to observe and analyze asteroids that occult distant stars. The second being to derive a shape of an asteroid observed occulting a star. And the last being to refine a pre-existing shape model of an asteroid. Now, my research was especially novel because of my low to even non-existent error in time for all of these observations. A large problem in the asteroidal occultation field is that many observers have large errors in time, rendering their observations null. But with the help of my mentor, I was able to overcome this common challenge and produce very accurate results. For my project, I had access to three different telescopes: an 85mm refractor, seen here at the top of the image, a 356mm telescope, seen here in the center of the image, and an 80mm solar telescope, seen here on the bottom of the image. Now, for all the asteroids that I'll be presenting on today, I used the 356mm telescope. And for recording the event, I used a Wattec 910 HXRC, seen here on the bottom left of the slide. Now, I use this camera because of its wide range of exposures that it can capture at, making it perfect for asteroidal occultations. Going back to the key programs provided by the IOTA, here is Occult Watcher. Occult Watcher tells me two main points of information: when the asteroidal occultation will occur, highlighted there in blue, and where the observatory is in the shadow path of that asteroid, depicted by the black line in the blue shaded region there. Now, the closer the black line is to the center of that blue shaded region, the more likely an occultation is to be a positive event. But it is sometimes favorable to be in the outer red regions because if an asteroid has abnormalities or has a moon orbiting around it, it is much easier to see such characteristics from those regions. The program that I use to control the telescope is called the SkyX, and the SkyX is a very simple program that uses a multitude of star catalogs to locate objects in the night sky. Here I was locating asteroid 105 Artemis, seen there in the center of the slide, and once I locked onto it, I simply hit Slew 2, and then the asteroid is tracked throughout the night sky. Once the asteroid is tracked, I can then move to conducting a PyMovie test or an exposure test. Now, the important information is seen here at the bottom left of the slide. And taking a closer look at that, I want to point your attention to two main points in this slide: the max pixels and the signal. The max pixels needs to be between 150 and 250 to ensure that the exposure is correct. Also, the signal needs to be between 1500 and 3000 to ensure that the saturation is correct. Once these two values are true, I can then move to observing and then analyzing the event. The first step in the analysis process is uploading the data to Pyote. Pyote then creates a flux by frame graph clearly showing the asteroidal occultation and the magnitude drop, seen here in the center of this image. Now, due to very clear sky conditions and a dim moon, these results were very clear. The same was true for asteroids 2132 Zhukov and 234 Barbara, both of which having very clear sky conditions leading to very clear results. But for asteroid 53 Calypso and 336 Lacadia, this was not the case, as there was a bright moon and lots of haze in the night sky. So to counter this, I ran a normalization of the data. Now, a normalization of the data occurs when I compare the reference star, depicted by the green dots, and the target star, depicted by the blue dots, and I average the two or divide the two out. Once this division takes place, it is much easier to see the disappearance and reappearance regions of the magnitude drop, so I can then record a positive event after this division is completed. The next step in the analysis process is uploading the data to Occult. Occult is a software that allows me to generate either an ellipse or a shape model of that asteroid, depending on how many positive observations were made. Here, for asteroid 105 Artemis, there were only 2 positive observations made on this asteroid, so I only was able to generate an ellipse, because a minimum of 4 positive observations is required for generating an instantaneous shape model. The same was true for asteroids 2132 Zhukov, 234 Barbara, and 53 Calypso, all of which not receiving the 4 positive observations required for generating that instantaneous shape model. But for asteroid 234 Barbara and 53 Calypso, there were 4 observations, but there were not 4 positive observations, as the top observer received a miss in 234 Barbara, and the top and bottom observers also received misses for 53 Calypso. But for asteroid 336 Lacadia, there was a pre-existing shape model in the DAMIT database, so I was able to use my observations along with the observations of the other astronomers made that night, and I was able to refine this pre-existing shape model. Now, overall, asteroids 105 Artemis, 2132 Zhukov, 53 Calypso, 234 Barbara, and 336 Lacadia were all positive events. And out of these 5 events, 4 ellipses were generated, and the shape model of asteroid 336 Lacadia was refined. Some limitations that I mentioned before in my study were visual obstructions. These visual obstructions included clouds, haze, humidity, and moonlight, all of which were present in the asteroidal occultation of 1,312 Vassar, seen here on the right of the slide. Now, due to all of these obstructions being present, I was unable to mark disappearance and reappearance regions and unable to conduct a normalization of the data as there was just too much noise. So, due to this, I had to record a null event or a miss. Also, there was a clear lack of observers for all of these events, as I was not able to generate an instantaneous shape model a single time, because I never had that 4 positive observations on any of these events. In conclusion, 2 out of the 3 of the study's objectives were met. I was able to observe and analyze asteroids that occult distant stars. I was also able to refine a pre-existing shape model of an asteroid, but I was unable to derive a shape of an asteroid observed occulting a star. Overall, these findings broaden the understanding of all of these asteroids, and since the data is already uploaded to the IOTA website, which is further backed up into the NASA database annually, astronomers can use this information to provide insight on the formation of dynamical families and terrestrial planets. This information can also be used to refine the asteroid's position and orbit, making the next occultation even more accurate. I'd like to thank my science research teachers for helping me through this rigorous course. I'd like to thank my mentor for helping me with this project and giving me access to the observatory. And I'd like to thank my family for driving me back and forth from the observatory when I needed transportation. Here are my references. Any questions?